All right, let's get started. Reminder again, December 8th is CSED week. We'll need volunteers. We'll also need demos. So please do consider doing both or at least one. Are there any questions on logistics before I go on? In case you have not checked PRs in the last couple of hours, I had asked the question of computing these p-values for the problem of when you're looking at the weighted interval scheduling problem. And it turns out you cannot do better than n log n, up to model of the constraints that if you're looking at number of comparisons that you need to do that. So Matt and Grant had an argument that's up there. After looking at the argument, I realized there was potentially arguably a simpler argument to do the same thing. So you don't have to waste any more time trying to figure out if you can get O of n time algorithm, because it's highly unlikely there exists one. All right, so we're looking at dynamic programming to solve the weighted interval scheduling problem. And now that we've seen one dynamic programming, I'd like to state kind of 3 rules of thumbs that you should kind of look for when you're trying to design a dynamic programming-based algorithm. The first one is there are polynomially many subproblems, and this is kind of a necessary condition, right? So if the number of distinct subproblems that you're trying to solve is already, say, exponential, your dynamic programming is not going to run in polynomial. So for the weighted interval scheduling problem, these were just the n opt values, opt of 1 up to opt of n. To remind you, these are opt of I was the maximum value you can get from any valid schedule for the first I intervals. The second is you should be able to compute the optimal solution for the entire input based on optimal solutions for the smaller subproblems. So in case of weighted interval scheduling, we derive the following recurrence, which says opt of j is max of 2 values. The first one is if j is in the optimal solution, in which case you get a value of vj. And then you are left with the problem on the first pj instances. And otherwise, if j is not, then the optimal value is the same as having j minus 1 intervals. And finally, there is an ordering among subproblems that allows you to come up with an iterative solution. So the last point is important to go from this recursive definition to an iterative definition. And for the case of weighted interval scheduling problem, this was fairly simple because we observed opt of j just depends on the previous j minus 1 values. Now, as we look at a bit more involved dynamic programming algorithms or problems, the ordering is not necessarily going to be so nice. So in the sense that it's not going to be like you lay down these numbers on a line and any value that you want will just depend on the previous values. But we will see another example where, morally it's still the same thing, right? So, and again, all of these 3 steps are crucial. If you don't define the correct subproblem, then you won't get the recurrence that you want. If you don't have the correct recurrence and subproblems, you won't be able to find a nice iterative ordering. So what we're going to do today is look at another problem where just as a warning, I'm just going to start off with an algorithm that's not going to be quite correct and look at a subproblem that's not going to be enough. And then we'll see how you need to modify the definition of the subproblem to make it work. Once we get the correct subproblem, the second and third steps are not necessarily that hard. Okay. All right, so we're going to look at a problem that in literature is known as the subset sum problem, but here's a potential application. So let's say you have n jobs, and let's say that the ith job takes wi cycles. Right? So you know how much time or how many cycles each job takes. And let's say you already have bought capital W cycles on the cloud. So maybe on Amazon or whatever is your favorite cloud service provider. And so then you can start asking questions like, what is the maximum number of jobs I can schedule given that I have these constraints and this total amount of cycles that I've bought? And then you can try to be a bit more ambitious and say, well, maybe what I really care about is not necessarily the maximum number of jobs, but how many of can I just utilize as much of my W cycles on Amazon as possible. Let's say they're just expiring, so you just want to get rid of them. And so these turn out to be slightly different problems. It turns out maximizing the number of jobs you can do with a greedy algorithm. But if you want to maximize the number of cycles you utilize, greedy algorithm is not enough, and we're going to design a dynamic programming-based algorithm for this. Are there any questions? Okay, so just as a heads up, we're going to forget about the fact that I talked about this Amazon cloud, which is, if you think of the problem, it's just n numbers, W1 to Wn, and another bigger number, capital W, and you want to schedule jobs so that you use up as much of the capital W cycles as possible. Okay. So, I said, so we're going to look at the dynamic programming-based algorithm for this, and again, remember kind of the 3 steps. Designing the correct subproblems, coming up with a recurrence, and then designing the correct iterative way to look at the subproblems. All right. So as I mentioned, this problem is called the subset sum problem. And so here's the mathematical problem that we like to solve. Your input are, say, n integers, W1 all the way up to Wn. And we'll assume that these are strictly positive. Okay. You're also given another integer or even a real number, another bound, capital W, which is non-negative. So it's greater than or equal to 0. And what you want to output is a subset of these numbers which satisfy 2 properties. The first one is you want the sum of the numbers that you pick to be upper bounded by this bound W. So you want summation I in S Wi to be less than or equal to capital W. And the second one is you want to maximize this total weight that you get, assuming it satisfies this bound. So it maximizes Ws, which is defined to be the sum of these values. So again, as a reminder, in the cloud service example, Wi is the number of cycles you need to do job I, and capital W is the total number of cycles that you have already paid for. Okay. And so again, you're trying to use up as much of this as possible. So let's look at a simple example. So let's consider the case when n is equal to 3, and say W1 is 1, W2 is 3, W3 is 3. And we'll consider 2 cases of this bound for capital W. If capital W is 7, then note that the sum of all the 3 values is less than or equal to 7, so it makes sense to just schedule all of them. Right? So pick all of them. All right. So in this case, solution or the output should be 1, 2, 3. Any questions so far? Is everyone okay with the problem statement? Okay, if there are no questions, then if I change the bound to 6, what should be the answer? You can talk to your friends for half a minute if you want. All right, I forgot your name. Sorry. Right, so in this case, you can take both 2 and 3, and that will give you a total weight of 6, which is less than equal to the bound of 6. Right? And this is the best possible thing. If you pick any other subset, if you pick all 3, then you're exceeding the bound of 6. If you pick any other subset of size 2 or smaller, it will have values strictly smaller than 6. Okay? So if you pick your S to be 2 and 3, it satisfies the property that the sum of the weights is less than equal to the total bound, and it is the maximum possible. Okay? Because again, if you actually have a solution where your total sum matches exactly the bound, you cannot do any better. So in this case, solution is 2 or 3. Let's take another example. What if W is 5? Samrita? Right, so in this case, you have 2 possible solutions, either 1, 2 or 1, 3. Both of them have value of 4, and it's less than 5. And this is a case where you actually cannot meet that bound. Right, so there's no way of picking a subset of numbers that will actually meet this bound. All right, so in this case, the solution is either 1, 2 or 1, 3. Okay. So I said there is a simpler version of this problem which is you want to maximize, so you again want this condition that the sum of the weights is less than equal to the bound, but now you want to maximize the number of elements that you're picking instead of trying to maximize their weight. Okay. Right, so what I want you to do is talk to your friends and come up with a greedy algorithm that solves this problem. Okay. Okay, any questions? All right, Mehmet, you have a solution? And sorry, what? When do you stop? So you're ordering from lowest weight to largest weight, and you go in that order, and then? Right, so the idea is you sort all the weights in increasing order, just keep on putting them in till you exceed this bound of capital W. Okay? Or put another way, you try to pack in as many as you can while you do not exceed the budget. And once you exceed the budget, you stop. Okay? All right. So, so sort by increasing WIs and pick as many as you can without exceeding the budget capital W. So let me call this, instead of a bound, let me call this budget. And you can prove this is correct by using basically, essentially the greedy stays ahead argument. The argument always will be if you have, if greedy has put in, say, 100 elements so far, it will have the maximum amount of empty space to the budget so far. Okay? So using that argument, and you can make this formal, which I'm not going to go through. So I leave it as an exercise. Prove this is optimal by using greedy stays ahead. To basically argue that at any point of time, the first I elements that greedy puts in, it will still have enough, still have more space left than it would for the optimal. So once we have this greedy algorithm, the first thing to try when you're trying to solve the mode, so we'll now go back to the weight case. And the first thing we should try, even though you probably can guess by now it's going to fail, is to try this greedy algorithm on the general weighted problem. So next, so we are going back to the original problem of trying to maximize the weight of the subset picked and not just the size. And so what you could try is use the greedy algorithm as above. And as you can guess, the reason and the reason why this would fail while trying to do the weighted thing is, again, the greedy, intuitively what it's trying to do is pack as many elements as possible. It is looking at the weights, but its objective is to just maximize the number of numbers or elements that you put in. So here's a simple counter example. So consider the case where actually we'll consider this set of weights and this capital W. So W1 is 1, W2 and W3 are 3 each, and the budget is 6. Now, if we look at the greedy algorithm, it's going to pick the one with value 1, W1, and then it'll pick either of the two with value 3. Right? And then when so it has, say, picked 1 and 2, and then when it tries to add W3, it won't be able to add because the sum exceeds the bound of 6. Okay? So greedy will output 1 and 2 in this case, which is not optimal because we've seen the solution is 2 and 3. Okay? So greedy outputs 1, say 1 and 2, or 1 and 3, but optimal is 2 and 3. So now you could try to say, well, okay, maybe it's failed, maybe there's another way to define a greedy algorithm. Maybe I do it in descending order or something. And it turns out it fails. And it fails in the sense that there are no known algorithms that solve, greedy algorithms that solve this problem. Okay. And I believe this might actually even be proved for a relevant subclass of greedy algorithms, though I'm not 100% sure. Okay. So I'll just keep it as a note. So I'm just going to say there are no known greedy algorithms for this problem. All right. So our goal now is to design a dynamic programming algorithm. And as we did for the weighted interval scheduling problem, instead of trying to figure out the subset that is the optimal solution, we'll just try to figure out what is the largest value of that solution that you could have. Okay? So, so in fact, so instead of trying to compute W of S for some optimal S. Okay. So again, we're just going to, instead of trying to figure out the actual subset, we're just trying to figure out its value. What is the best possible value you can get? And again, like with the weighted interval scheduling problem, once we design the dynamic programming based algorithm to figure out what this optimal W of S should be, you can recreate the actual set S also. Okay. All right, so as before in the weighted interval scaling problem, instead of looking at just the optimal solution for all n values, we're going to look at the optimal solution for the first, say, j, for every value of j. So let O of j be an optimal solution for W1 all the way up to Wj. And you define opt of j to be this way, right? So this is the best value you can get out from the first j elements. Before I go on, are there any questions? Is everyone okay? Okay. So as we did for the weighted interval scheduling problem, we're going to try to see if j is in the optimal solution from 1 to j or not. And in both cases, we're going to try to derive an expression for what opt of j should be. And then we'll combine both by using a max operator. So case 1, let's assume j is not in the optimal from 1 to j. In this case, I claim that this is also an optimal solution for the smaller problem where you don't include the last guy. And the argument will exactly be the same as we did for the weighted interval scheduling problem, we're going to say for the sake of contradiction, let's assume there is a strictly better solution from 1 to j minus 1, and then we'll observe that you can use that for a solution from 1 to j as well. So the claim is O of j is an optimal solution for 1 all the way up to j minus 1. So I'm looking at the first j minus 1 numbers. And I said the proof idea is proof by contradiction. Let's say O prime is a better solution from 1 to j minus 1. That implies O prime is also a better solution for 1 up to j. Right? So the point is, if you have a solution that works, is a valid solution from 1 to j minus 1, it will also be a valid solution from 1 to j. Okay? And we have already argued for the sake of contradiction that the weight of O prime is strictly bigger than weight of OJ. And so maybe I should clarify, when I said is better, I meant it's better than the solution which is optimal for J. Yeah, Tyler.
So when you're saying J is not necessarily the optimal solution, but the optimal, I'm kind of confused by case one statement. What you're saying.
Oh, what I'm saying is, if it is, so there can be only two cases, either J is in the optimal solution or not. I'm saying if it is not, then it has to be case that the best value weight that you can get from 1 to j is same as the best weight you can get from 1 to j minus 1. Any other questions? So in fact, this is exactly the same equality we had gotten for the case weighted interval scheduling problem, but the last guy was not in the optimal solution. All right, so let's look at the second case. So let's say now that J is indeed in the optimal solution. And so, like weighted interval scaling problem, we'd like to argue something about what about the subset of numbers where you drop J from O of J, right? And so can we say something about that what remains is actually also an optimal solution for a smaller subproblem? So question is, what can we say about the optimal solution by dropping the last guy? And the hope is you want to say something like, in this case, that this is also an optimal solution for a smaller instance, let's say J prime, where J prime is strictly smaller than J. So this is what we'll hope for if we have something like this. If so, we can get something like opt of J is the weight of the jth guy because you're picking that, plus the opt of J prime because that's it's optimal for the smaller instance. Okay? So this is what we hope for. And as I told you earlier, this algorithm, I'm going to start off with something that's not correct, so this doesn't work. So talk to your friends for half a minute, and try to figure out where we went wrong. So I claim in particular that our definition of subproblem is not good enough. In particular, you want your subproblem not only just to depend on J, but something else also. Does the question make sense? All right, are there any questions of what we have done so far? Okay, if not, so why is this definition of opt of J not enough? What are we missing? Matt? Right, so the point is, I said opt of J is the optimal solution for, where did I write it? W1 to Wj. But this is not my entire problem, because my entire problem, not only does it need these values of weights, it also needs this budget. So in particular, when I'm defining O of J to be an optimal solution for, for W1 to Wj, I'm just completely ignoring the budget altogether, right? So in some sense, I'm not looking at a sub-problem of the original problem, because I'm not keeping track of budget. So in particular, what we need to do is also, when we are trying to design the sub-problems, we also need to keep track of how the budget changes, right? Now, in the case where we are not, if J is not in opt of J, we are good, right? I mean, we are not adding anything, so the budget doesn't change. But in the case where we are saying that J is in the optimal solution, then we have to keep track of budget. And here's essentially a quick thing by picture. So let's say I originally had a budget of W for my problem from W1 to Wj. So that's the budget that I started off with. And I'm saying in this case, J is in opt of J. So what that means is, I picked this jth guy that has weight Wj, right? So if I'm looking at the instance where I say, or put another way, if I pick J, how much of the budget remains to put the rest of the stuff in? This is not a trick question. Sorry? So the question is, if I pick Wj, and I'm saying it is in my optimal solution, and somehow what I want to say is, I want to handle the remaining sub-problem, how much of the budget remains, given that my original budget was capital W and I picked J? Yes, so the remaining budget is you already have used up little Wj, so whatever remains is the difference. Right? So in particular, the new budget is essentially what remains. And so what this says is, when we are trying to define a sub-problem, it is not enough to keep track of the value J, but you also need to keep track of how much budget remains. But so you need to keep track of both of these. And so it turns out this definition turns out to be enough. So the solution, keep track of budget and value of J. So in particular, I'm going to define opt of J comma B to be the weight of an optimal solution on the numbers W1 to Wj and budget B. So I'm keeping track of both how many of the first J numbers I'm keeping track of, and as well as how much of my budget remains. So let's go back to the case that the jth number is actually in the optimal solution from 1 to J. And so somehow I want to argue about So again, I'm looking at the case where J is in the optimal solution and my budget is B. So if I pick J in O of J, then I'll get the weight of the jth chi. And then I'm looking at the optimal solution of the case where my budget has now decreased from capital W to capital W minus Wj. And how many numbers remain? What should be this quantity? J minus 1. So I've just taken one guy out. Okay. So I claim this is almost correct. There's a corner case that you have to handle. So this equality that I said doesn't quite work for one corner case. And if you see why, when this won't be true, as a hint, remember that the budget has to be positive. Right, so what you have to, since the budget, oh, sorry, this should be B. And since this remaining budget has to be positive, in here it cannot be the case that Wj is strictly bigger than B. Okay. So we also need so in particular, it's saying if Wj is strictly bigger than B, it can never be the case that you're going to pick it in the optimal solution, just because that number by itself is exceeding your budget. So let's kind of go back to case 1, just because we have changed these, I've changed the subproblem on you. So here we're looking at the case that J is not in the optimal solution. And again, in this case, so I started off with opt of J comma B. And since I'm not picking anything, my budget doesn't decrease. So what should this first parameter be? J minus 1 again, right? Because I picked one element, I have one less to go. All right, so now what we do is just let's pull everything together, and our overall recursion would be, so again, we have to also make sure that handle the case when this is not happening, right? So if Wj is strictly bigger, sorry, I've changed notations in a bit, but I just want to remind you, originally we had W, so I'm going back to W again. So if Wj is strictly bigger than the budget W, then we have in this case opt of J comma W is equal to opt of J minus 1 comma W. Else, we have either this case or this case, and then we'll just take the max of both. Okay. Else opt of J comma W is max of Wj plus opt of J minus 1 budget W minus Wj, max of this, and opt of J minus 1 comma W. And so we're done with the second step. Now we have designed a recursive formula for the optimal solution, and we have defined this subproblem that we're interested in. Talk to your friends for half a minute. Let me know if you have any questions on this recursion that we came up with. Okay? So I want you guys to be comfortable with what this recursion is saying. All right, Mehmet, you had a question?
So back to the first time you mentioned case, you said that we were doing some sort of contradiction.
Are you talking about somewhere over here or the previous page? Over here? Yeah. Okay, so let me restate the proof idea now for the correct version of the subproblem where you also have the budget of W. Okay, so what the proof idea is saying is, so we want to argue that if J is not in the optimal solution from 1 to J, right? Then we want to argue that that is also an optimal solution for 1 to J minus 1 with the same budget. So that's the part that was not there because we're looking at the wrong thing. And the argument is, assume that is not the case. That is, O of J is not an optimal solution for the first J minus 1 and the same budget. Then if that's not the case, there has to exist some other solution, say O prime, that is strictly better, has a larger weight, but also is still within the same budget. And now the fact that I have a subset from 1 to J minus 1 that is within the budget W means if I pick the same subset, it will still be a valid solution for 1 to J and the same budget W, right? Just because, I mean, I'm just not picking J, right? So I'm still valid. And so that means I have a valid solution from 1 to J with budget of W, which is strictly better than O of J, and that contradicts my assumption that that was optimal. Any other questions? Mark.
What about when you have to throw something away from one of the steps?
What do you mean you have to throw away something?
So in your case when W6, about that.
Okay.
So in the case with W6,
Uh-huh.
go through that stuff at 2, you're going to have 1 and 3 in your set.
So let's say you're looking at, so you're seeing whether 3 is in the solution or not. Okay, and you're assuming, let's say it is not, or it is.
Let's say it is.
Okay, let's say it is, all right.
That would be W3 plus opt of J minus 1, which would be 2.
Right.
But opt of 2 is 1 and 3.
No, because the budget is going down from, oh, sorry, yeah, that's fine. Okay, so W is 6, so you go down with so now you have a budget of 3 and you have 1 and 2. Right, that is why it's crucial that you have that we have this budget component. Otherwise, you're right. You just Alex.
What's the data structure that represents opt look like?
Awesome. That was going to be my next thing. So, but any other questions? Okay. So remember, last time we had just opt with one parameter, and so we represent it as an array. And I have 2 parameters, so we're going to represent it as a 2D array or a matrix. Okay. So we're going to have a matrix where the rows are indexed from 0 to capital W, and the columns are indexed from 0 to n. And so let's say I call this matrix M. And so if I look at any row corresponding to a budget B, and any column corresponding to the number J, then M of Bj would be same as opt of J comma B. And over here, again, J is from 0 to N, and my budget is from 0 to W. Okay. So if for another dynamic programming algorithm, your opt had 3 parameters, and you're looking at a 3-dimensional array, and so on and so forth. Okay? And the idea ultimately would be we want to fill in this entire matrix. So that's what the algorithm will do. Okay? But before we do that, let's kind of go through the 3 steps that we want from like the 3 rules of thumb. So the first one is how many sub-problems do we have? Mehmet. Sorry? Is the size of the matrix. Right? Because every entry in the matrix corresponds to one sub-problem that you want to solve. Alex?
Is it W times N?
It's n plus 1 times w plus 1 just because I'm starting my indices from 0. So it's w plus 1 times n plus 1. So in particular, if w is not too large and it says polynomial in n, then this is still polynomial size. All right, so the second question is, if I compute this entire matrix, what is the final value? Which entry in this matrix are we really interested in? Mehmet? No, so again, remember my original input had n numbers and my original budget is w. So you want n comma w, right? So the second question was, what entry do we want? And we want m of wn, which is same as opt of n comma w. Okay. So this is the entry that we are interested in, but it turns out to figure this value out, we'll just compute this entire matrix. And of course, if we compute the entire matrix, we'll just read off the top left column, and we'll do it. So the third question is, we want to come up with an ordering so that, in that ordering, if we just point to a subproblem at that point of time, I should be able to compute it from if I know all the values that come before. Okay? And how do we figure that out? The idea always is, let's go look at the recurrence relation itself. Right? So we're interested in, say, so let's say I'm interested in opt of j comma b. So I'm interested in this thing. Then the thing to note is that it could be dependent on with the same budget, but in the previous column, right? So this can definitely depend on the value in the same row, but in the previous column. Or it could be a value in the previous column where the budget is now smaller. So there could be an entry corresponding to b minus wj. But these are the only two other values that this b comma jth entry will depend on. It's either the very previous guy in the previous column in the same row, or there's another guy in the previous column but with a smaller value. And this is the only dependence, right? So that's all you need to know. So given this, do you guys see a way of kind of iterating it so that you can always have the values that you need ready the moment you need it? Any guesses, thoughts? Would going row by row work? So what I'm saying is, what if I compute, say, this row first, and then this row, and this row, and so forth? Would that work? No. It won't work because you won't know this value when you want to compute this value. However, if you went column by column, you're good, because every value in this column just depends on the previous column. Okay, so the ordering is go column by column. So we'll look at this more detailed next Monday, but the idea is you just kind of move column by column. All right, have a good Thanksgiving break, and I'll see you guys in a week.